This is Design Safe Radio, where natural hazards researchers strive to make our society more resilient to everything nature throws at us.
Hello and welcome to another episode of Design Safe Radio. I'm your host, Dan Zahner. Super excited to be with you once again and talking to a colleague of mine that I haven't had the privilege of meeting yet, but I've been following along with her work for the past few years as she's part of the Tallwood team that has been working on this amazing project we can't wait to tell you about since at least before 2017 when they had the first edition of Tallwood out at the UC San Diego Shake Table, where my friend Keri Ryan is at today. Keri, it's nice to meet you.
Nice to meet you.
So tell us a little bit about yourself and your research. It's just really cool what you guys are doing down there.
Yes, I am a professor of civil and environmental engineering at University of Nevada, Reno. I have been at UNR for 12 years, and I have been doing seismic engineering type of research my whole career. I sort of had my roots with seismic isolation, which is a type of protective system that's very good at protecting buildings and bridges and infrastructure from the effects of earthquake. I've kind of expanded out more recently with a focus on non-structural components, which I think in many ways is not unrelated to the original field of seismic isolation. So I am really excited to be part of the Tallwood team. And we have been planning this test, intensely planning for the last 2 years. So it's really exciting to see it come together.
Yeah, the Tallwood test is just unlike anything I've ever seen. I mean, it's a full-scale building in a way that, like, you know, from a not a structural engineer person who's not familiar with this way of seismically isolated buildings, it looks incredible. And from the first small scale test, this one I think is going to be really amazing. So can you tell us a little bit about the NHERI Tallwood project? This is a huge team working on a huge we keep using the word huge, but there's just not another word for it.
Yes, it's a large team. There's a lot of people involved. The overall scope of the project, we are constructing on the seismic shake table at UCSD. We are constructing a 10-story Tallwood building made of mass timber components. And so what we mean by mass timber is like engineered lumber, large beams, large panels that are engineered to have specific properties for different actions. And we can only go so tall with typical light frame wood systems because you just can't get enough strength and resistance. So mass timber allows us to go taller with wood. One set of rocking walls is built with mass plywood panels. And so, just think about different plywood strips, I guess, glued together, etc. When we originally started this project, our vision was cross-laminated timber. Cross-laminated timber are boards that are basically, like, I have a visual.
Excellent. Love visuals.
Here is a visual of a mass timber panel and how it's built. So it's boards aligned in one direction and glued together, and then the next layer aligned in the other direction and glued together. And the neat thing about CLT is it gives you kind of resistance in both directions. Mm-hmm. So that was our vision, that we would use primarily CLT in the building. At the end of the day, CLT is more expensive, and we had a harder time getting the donations. We got donations from a lot of different vendors, different products. So we are using not only CLT, but the mass plywood panels. We have one set of rocking walls is CLT, one set of rocking walls is the plywood panels.
Oh, interesting.
Yeah, I have another visual also for floor systems.
Oh, cool.
Okay, so we have in the floors of the building 4 different types of floor panels. CLT by Mass Timber Services, glue laminated timber by Mass Timber Services. Glue laminated timber, from what I understand, is like a two by whatever that are oriented vertically and glued together. That's the GLT.
Okay.
Nail laminated timber, dowel laminated timber are the same, except the boards are nailed together or connected and fastened with dowels, like shown here. And then the last is veneer laminated timber by Boise Cascade, the top 4 stories. And that's like a plywood, massive plywood panel. Again,
Yeah,
I think is the best
just
way to
a
describe
whole lot of veneer glued together. And these floors are how thick are these floor panels?
Depends. They're varying thicknesses. They start at around 6 inches, 6 to
Wow.
8 to 10, I believe. Yeah.
Yeah, just to kind of give a sense of scale, because the scale model gives you this idea that, oh yeah, it's this small thing, but it's a building. So normally this would be poured concrete, right? Like 4 to 6 inches of poured concrete or something.
Right. Yes. And normally I think you would still have a topping layer of gypcrete or something like that. Ours is pure wood, and you can almost see from this this diagram here, there's little straps across all the floor panels to because they're manufactured, and then the straps are used to collect them and transfer the loads so that they can function as a diaphragm. And every type of floor system that we have here has different strapping details. When we walk through the building, those aren't going to go away. You have to kind of watch your step because there's these straps. Yeah. So in a real building, you'd have to do something to finish the floor, but ours is going to be a little bare. And we can see what happens.
But yeah, it makes it so you can see what happens and also disassemble it at the end a little bit easier.
Right. So I think we should backtrack, and I want to talk about the overall concept of.
Yes. Yeah, we've gotten a little bit down a rabbit hole because this is so exciting, which we tend to do, right? So as we're backtracking, so this is all from a whole lot of partnerships all together in just this Tallwood idea. So yeah, let's backtrack to there. There we go.
I explain the overall concept of what we're trying to achieve with the test. So the main goal of the test is to develop and validate a new type of lateral system. And what we mean by lateral system, the way that the structure resists the earthquake from lateral loads, wind and seismic. So ours is the wood panels are designed to be a rocking wall system. They are not fixed to the base. They are designed to rock up off the base. And I mean, that's good because they naturally want to, and the rocking motion allows the movement to be accommodated without damage. But in order to support that rocking motion, there's several details that are important. The entire walls are post-tensioned from the base all the way to the top, post-tensioning strands. And when it rocks up, they provide like a restoring force to help it keep it from totally rocking over. Wow. Also, another detail that we see. So first of all, you either have a set of coupled rocking walls, like in the 2-story building that you recalled from a couple years ago. There were 2 sets of walls that were kind of connected together. We opted for bounding columns. And yeah, so you can see there's the rocking wall panels and the bounding columns. And connected between the rocking wall and the bounding columns are these UFPs, U-shaped flexural plates. So as the whole system rocks, those plates deform and dissipate energy. And dissipation of that energy helps to limit the overall movement of the building. And then the last piece is the way that that the wall is connected into the diaphragm. And this shows, hopefully you can see or understand this graphic. Floor panels connected into the wall system. We call it a shear key, but it's fastened in like this a lot of steel hardware. Okay, this massive steel plate with a extender beam, the beam is extended through a slot in the hole of the wall. So it allows the wall to rock up without taking the floor with it. And that's good because if the floor, rocked up with the wall, then it would be subjected to this distortion and so on. It would get damaged.
Right.
So this connection here is carefully designed to prevent that from happening.
Wow. So you've got that going on for 10 full stories. That is just
Yes.
bonkers.
Yeah. It's a lot of steel hardware, a lot of detailing to get this.
And so, and your part in this transition to where you fit in is the non-structural component. So we talked a bit about the structure,
Correct.
how the floors and the walls and the diaphragms and the energy dissipation elements, but then you get to things like stairs, like, and the things that make a building livable in that are not part of the structure but still extremely important. So what are some of those components of the building and the questions that you're hoping to answer about those?
Non-structural components is a blanket term, basically represents all parts of the building that are important for its function, but not part of the load resisting systems, not part of carrying the gravity loads or the earthquake loads. So examples of non-structural components include non-structural walls, stairs, elevators, ceiling system, piping, equipment, any mounted equipment, etc. There's quite a number of different types of non-structural components. The earthquake engineering community historically has focused mainly on structural design, and we have a pretty good handle on that and what we can do to minimize damage in the structure and prevent collapse or even get better performance. But in past earthquakes, a lot of the damage is focused on non-structural systems. And I think the last major earthquake we had in the US, the Northridge earthquake in 1994, majority of the damage was non-structural. And that really got everyone's attention. And so we have started to focus a little bit more on non-structural components. So for this project, the team knew they wanted to have an emphasis on non-structural components as well. And it's a great opportunity. So I was recruited for that role, and I kind of had an open book. What do you want to do here? And we decided, since it's a flexible building, Tallwood, we wanted to focus on drift sensitive components, those that are basically connected floor to floor and therefore get subjected to the lateral movement of the building. So we focused on non-structural walls and stairs. I do want to acknowledge my students from UNR, my 3 PhD students. They're all on site here today as well. William Roser, ENG, and Sir Lathan Wynn. They're wonderful. We couldn't do this work without them.
Glad you mentioned that, because a lot of the kind of grunt, tedious work of these big projects is done by the graduate students.
Absolutely.
And we couldn't do any of this without them. So you've got stairs, you've got cold form steel, non-structural walls. Do you have elevators in this building as well, or just the stairs? Okay.
Just the stairs.
I mean, just the stairs. But
just the stairs. The stairs are essential, of course, so why not make them part of the research?
Yeah, exactly. So what are some of those big questions you're hoping to learn about those pieces in this shake?
Right. You mind? I'd like to describe our exterior wall subassemblies. So go ahead and share again. This is a Revit model of the bottom stories of the building. The Revit model was done by another student from Colorado School of Mines, Alicia Bush, who works for Shiling Pei, who's the PI of the project. So we decided to do, we didn't have the resources to clad the whole building. We decided to focus on sub-assemblies, what we call sub-assemblies, each one detailed a little bit differently so that we can compare how they perform. And each one of them is designed with some thought to how we can accommodate the movement in the building. One on each corner, basically. In the next visual, you see kind of a snapshot of a single story. So 3 of the sub-assemblies are cold formed steel framed. They could also be wood framed, but the cold formed steel industry was interested in participating in this test. So that was
go with where the resources are sometimes.
Exactly. So we labeled those cold formed steel sub-assemblies. We labeled them CFS1, CFS2, CFS3. The first one is platform framed. The second one is bypass framed. The third one is spandrel framed. I'll explain a little bit more about each of those. And lastly, we have a stick-built glass curtain wall. So this is how these work. CFS1, the first one, is an L-shaped subassembly on one corner of the building. It is platform framed, which means that it bears down on the floor below. So it's connected, singly connected, separate units floor to floor. And the way we allow it to move is by having a slip joint at the top of the wall. And there's 2 different, basic CFS framing. You got a track on the bottom, a track on the top, and then studs connected in between. You can kind of see the outline.
Kind of like a big French door.
Yeah. So if you connect everything rigidly, it's not going to move. It's going to get damaged in the movement.
Right.
So a slip track, we call it a slip track connection at the top, allows the relative movement. Basically, it's a form of seismic isolation. Back to my roots.
Yeah.
We're isolating the wall, the non-structural wall, from the movement of the building. Okay, so the one way that we're exploring is, we call it a double track. So you have 2 tracks at the top, they're nested, and the slip occurs between the 2 tracks. They're not connected together.
So just like a sliding door.
Yeah, that's one detail. And then the other detail, this is a product of Semco's. It's a slotted slip track. So there's slots in the track in the top. So, and it's going to be connected through screws into the slab, but not, tightly connected. And
so those screws will ride in those slots.
Exactly. The slip is designed to occur between the floor slab itself and the slots. Now, what happens at the corner? Because this visual down here gets a nice visual of the problem. When you accommodate the slip in plane, there is an incompatibility with what happens out of plane.
Right, you got a big space in the corner there.
The corner wants to open or close. So that's where CS Groups comes in. They make a series of, they have a wide variety of different expansion joints, and we are using one of their expansion joints at the corner to accommodate that movement. Okay, the second one is a bypass frame system with drift clips. Bypass frames means that instead of bearing on the floor below, the whole system is like hung on the outside of the building. So, yeah, it's hung from those floor panels. And if it's rigidly connected, it's not going to move in an earthquake. And here's an image. We're going to use Simpson Strong Ties, one of Simpson Strong Ties products here, this DSS CB clip. It fits into, apologize, this is not a wood slab, it's visual, but it's utilized in wood. And they did a test for us to kind of understand the capacity. There's a unistrut attached to the floor slab, and then the clip sits in the unistrut and is attached to the stud. And the clip can slide in that unistrut.
Oh, wow. Okay. So that whole big panel can move and slide around in that strut system.
Correct. So on this one, we designed 3 stories bypass framed, which is a lot, because the expected movement over 3 stories is about 10 inches.
Wow.
And we went for the gold here. Like how tall of a bypass unit could you get to be successful here? The sketch by my student William Roser illustrates what happens when at the
Whoa.
corner over this 3-story unit, right? The drift gets, or the displacement incompatibility gets larger on each story. So for this one, we're using another expansion joint from CS Group, XLP2G1400, and it accommodates. It's like a door system almost. They have some illustrations on their website of how this one works. It's like it can pull apart, or if the joint pushes together, like the door flaps out, like shown in this image on the left.
Really cool.
Yeah.
So
yeah.
For those who are listening on your favorite podcast app, like go to the YouTube video of this, because Keri's got slides of all this stuff. It's just really fascinating.
The third one is the trickiest. This one
what in the world? Wow.
We call spandrel units and ribbon windows. So I think for architectural features, if you're going for a certain type of look, someone might use this system. So
there's
basically
these big wide plate glass windows, and you've got kind of 3 different orientations of being able to wrap around. I'm thinking like, corner offices and rooftop bars and things like that. Like this could be in structures like that eventually.
Yeah, and I think that for certain forms of architecture, this type of construction is very common. So as you said, the spandrel units are like the wall framing are attached back to the floor slab. And then there's one of those at every floor. And then between those units, we have a row of windows, a strip of windows. So how do you accommodate the movement in this one? By necessity, these spandrel units have to be attached rigidly to the floor slabs. And in fact, they have to have 2 points of attachment to prevent them from like rotating.
It looks like a combination of the past two. Solutions in a way.
So to accommodate, we have a slip joint at the top of the window and all around. And so the spandrel unit's going to stay rigidly attached to the slab. All the drift is going to occur over the window unit itself. And you have the incompatibility of at the corner. We use a similar joint. Well, let me backtrack a little. We do not have a joint on every floor for this one. We did want to see kind of what happens at these corner window units. They have some ability to accommodate that movement at the corner, but not a ton. I think they will say about a half inch or so. So we want to see like, how far can you?
So you're gonna let one of them break.
But I admittedly, this is our most vulnerable system. At the second story, we wanted to see, and so my graphic doesn't represent it well, but we wanted to see if we could protect the window unit with a joint. So we have CS Group's expansion joint similar to what we used in CFS1 at the corners of the second floor only. So what we're expecting is that the second floor will perform a lot better. Our last subassembly is the glass curtain wall, as I mentioned before, is supplied by Technical Glass Products. And it's a C-shaped subassembly on one corner of the building. Yeah, curtain walls in general are built from typically aluminum framing. They call them mullions, horizontal and vertical mullions, with a glass set in between. And the framing itself is designed as a racking system. Like the joints are not rigid and can accommodate deformation. So the whole system can rack without a lot of damage. And then the glass is fit into in between the framing units with a little bit of clearance. And so this visual here kind of illustrates what happens. The glass can actually rotate within the frame. And glass curtain walls have been reasonably well studied. Ali Mamari from Penn State has done quite a bit of research, and they have a racking facility They do unidirectional testing of mostly planar units. So our question here is, does a more realistic system under more realistic shaking perform as expected, or there are some things we've been missing from the unidirectional racking tests?
Wow.
So that's the last system, and we expect that we hope that it will not be damaged out to the drifts that we expect for the maximum earthquake in this building.
But that's why we test it, right?
Yes.
There's a whole lot of uncertainty that, at least for now, we can only accommodate by doing this in full scale, real world.
Yes. I'd also like to mention that Technical Glass Products has a special system that's fire rated, fireproof. And they have like an inch and a quarter, I believe, thick glass. So very, very heavy glass panels.
Wow.
They use steel framing rather than aluminum framing, and it's a very, very robust system. So this one is actually complete on our building. It was, I think I mentioned or alluded to the fact, Long's Glazing and Door had been installing that over the past couple of weeks, and they just finished on Monday.
Oh my gosh, I can't wait to see it. Oh, that's so cool. So along with all these, if you're like me, just drooling at all this. So
I am, trust me.
Yeah. So if you're listening along and going, oh man, this is amazing. So they actually have a live look-in video system at UC San Diego. We'll put the link below in the show notes for all these so that you can look and see what's going on any day that Tallwood is on the shake table. And they have multiple views, and there's a lot going on here. And as we've alluded to, it's not just the structural components, it's not just the technical parts of the non-structural components, but there's some architectural value to other fields. Can you talk about some of the ways that Tallwood and the Tallwood Design Institute, that is working with all of your partners, is working to help work with different fields?
Correct. I think, one of the great thing about the non-structural scope of work of this project is that it does overlap into architecture. And so we have attracted different partners on the project that probably normally wouldn't be so in tune to seismic issues, but are now in tune to seismic issues. And we do have some architects on the project, and they advise about these exterior subassemblies, and it's all architectural, really. Most of the needs in exterior subassemblies are driven by architecture, architectural concerns, and so on. I didn't mention we also have a number of interior walls, and it's similar architectural concerns as well, but functional concerns as well. So I think that's the main way that with this project, we really are expanding the audience of people that will be tuned into seismic issues and taking a little bit more consideration of that into the design and detailing.
Yeah. One of the great things that is coming out of this project, and the Tallwood Design Institute just had their mass timber research symposium last week up in Corvallis, Oregon, and I got to go up there and see some presentations by our colleague Barb Simpson was one of them, and she talked about the data reuse opportunities from this project and other follow-on ones that, for those who aren't going to be able to be in your research team, they can still use what you guys are putting together for their own research questions around mass timber buildings, tall structures. Can you talk a bit about that opportunity for data reuse and building your own numerical models as you're doing your research?
Yes, correct. As you know, all of these projects funded through NHERI must archive all of our data in DesignSafe. For this project, we'll have at least 750 sensors, different sensors to record the movement of the building, to record the drift, to record the accelerations, and for the structural system, there's some other things they want to measure, load cells to get the post-tensioning forces, and so on. For our purpose, my group, what we're really interested in is displacement transducers to measure the slip and measure the movement across joints and to see that they're working like we anticipate. So that's what we're hoping to gain out of that. I think when you record that much data for a building, it's overwhelming. It's overwhelming.
Yeah.
And there's I have been involved in a large project like this in the past, and sometimes it's hard for the research team to really make use of all the data that we record. And so there will certainly be opportunities for others who want to try to model the structure or look at the performance of the different non-structural systems, do non-structure and non-structural interaction type studies. All the details will be available and the data will be available following the conclusion of this project for people to make use of.
Thank you so much for listening to this episode of Design Safe Radio. We really appreciate it. Smash that like button if you're watching this on YouTube. Hit that little subscribe button. That really helps us out and bring this message to more people who are interested in hearing about how our engineers and scientists are making our society more resilient to everything nature throws at us. A big thank you to our sponsors at the National Science Foundation. Our award number is 212-9782. And a big thank you to our program officer, Joy Kowski, who is excellent. And our team at the National Science Foundation's Network Coordination Office for NHERI. Marty LaChance is our question writer and copy editor extraordinaire. Raquel Ruiz manages all things technical and editorial. And Morgan Glass is our social media coordinator. Big thank you to everybody at the NHERI NCO and all of our experimental facilities. Thank you and have a great day.